Welcome to the video on the Martinagle representation theorem. So in this video, we start with chapter 6, where we try to find representations of martingales in terms of stochastic integrals. Okay, so here, this is crucial. So we consider a Brownian motion. Right, as usual, so B is a Brownian motion, and we want to consider the Brownian standard filtration. We always did it, but here I would like to emphasize this again, because here we try to understand martingales which are measurable with respect to this Brownian standard filtration. Brownian standard filtration. So this means it's a right continuous filtration, which is completed with all the null sets, and the underlying probability space, of course, is completed as well. Filtration. The first aim is now to understand how we can represent martingales, random variables, which are in L2. So briefly, our aim is to say, okay, I have a random variable xi, which is in L2 and measurable with respect to the Brownian standard filtration at time capital T. Now my claim is, this is the main work for today, in this video, is to say, to prove this implication, which says there exists actually a way to represent this random variable psi as its expected value plus a stochastic integral from 0 to t, and then you integrate adapted process phi with respect to the Brownian motion. Right? And if we have this type of representation, it's rather simple to show that if I have a martingale which is an L2, then I can always represent it as a stochastic integral. Okay, so to achieve this goal, we need to consider a complex value stochastic process. With complex valued stochastic processes. Okay. Or in the end, E2 processes. So as we want to study Fourier transformations or characteristic function, depending on your background in the setting, right? So this is a stochastic process which takes values in the complex numbers. There's no reason to be scared because everything works as before. So if you want to integrate, let's say, from 0 to t xs with respect to ds, well, we just integrate the real part of x against ds plus I. So this is the and then I will integrate the imaginary part with respect to ds, right? And the same we can do for the stochastic integral. So if you want to, this process is adapted with respect to the Brownian filtration, then the E2 integral is just given, well, at the same representation. Again, I integrate the real part, which I know how to define, against the Brownian motion, and the imaginary part of x with respect to the Brownian motion. All right, okay, this is just a convention. Such we have E2's formula, right? So because this, we basically like defining the Should I say integral with respect to an iter process? Well, this is the same trick, right? We define it for what we know, and then since we did it in a linear way, all the results basically transfer to this complex setting. So why do I want to do so? Because, well, I would like to use E2 formula to apply to this functional, which is the exponential of I times u. U is a real number. So use a real number. And then I have plus. So I will look at to consider this functional, and I want to apply E2's formula. So let's do so. Okay, and the initial time 0, this is, well, this is all 0, so this means there's just 1. And then, as I said, E2 formula holds as we expect. So we have u I times u, and then, well, expect the exponential of what we had there. This is just the first derivative. Yes, u with respect to b. Okay, we get the second derivative, so plus 1/2. And then I have here I times u to the power 2, right? The second derivative, and then the function again. So nothing's really special holds here. And, well, then I have the part which is with respect to the time derivative, right? We have here time depends, so we need to apply the space-time E2 formula. So we get here the time derivative. So this is u squared divided by 2 multiplied with the function. Here. S divided by u dt. Oh, this is also dt. Okay. The nice thing is here, if I have I to the power 2, this is just -1, right? So these last two terms, they just cancel. Right, so here we go. So what do we get? Well, we have 1 plus t iu. Right? Okay. So why is this interesting? Right? I mean, okay, I did here this cute calculation. Well, the nice thing about this is if I rearrange it, okay. Do it correctly. Right, so let me put this on the other side. So I have an exponential of minus u square half plus u times exponential bts. Oh, okay, that's not good. Here's an s, here's an s, here's an s. Right, we integrate with respect to s. Yes, plus bt, right? Yeah, should be fine. And, well, this is what we know. I mean, right, this is nothing else than the expected value of exponential of I times u bt. Right, this is a characteristic function of a normally distributed random variable, which the Brownian motion at time t is. It's nice. And here we just copy what we had. Right. All right. Okay, Okay, now you say, okay, well, why did I do this little calculation and was so happy about it? Well, because this was our aim, right? So where you go? We wanted to have a random variable, which is L2, okay. The random variable we consider here is certainly an L2. So from this psi, I wanted to represent it as the expected value of it plus an interesting integral with respect to some integrand phi, which I somehow need to find or show the existence. And this is exactly what we have here, right? This is the expected value of a random variable psi. So what we have here, this is psi, this is the expected value of psi. And let's call this here phi. So we have here integral of phi with respect to Brownian motion. So we represented this random variable, which is in L2 because the Brownian motion is normally distributed, exactly as we wanted to. Cool. But now the main point is where we need to somewhere extend it to basically all f t measurable random variables. Okay, this is an approximation argument to extend it from this class of random variable to a more general one. Okay, this first step, we can basically redo the calculation and use the product rule to get the following lemma, which you're invited to do on the problem sheets. So let's take a natural number and we take some points, T1 up to Tn, P and U1 up to UN, R. And the point is then exists psi, which is in H2, such that we have the following representation. So if you take the product from J to N of integrands of this form, right? This is basically the functional we just considered, plus the square t dp minus 1. This is equal to 1 plus something for some phi, which of course looks a bit more complicated because, well, we have here the product of functions which are of this form, but in principle, I mean, this is possible. Okay. And this is proof. See problem sheets. All right. In particular, okay, this is easy because this is okay. This is doable. This means we have an integral representation for all random variables in, let's call it S. So which are somehow a linear combination, so in the span of these products. Right. Here we go. So what did we do? I mean, we just take this here again on the other side. So as we have done here, right? So this type of functionals are fine. So for this, we have already integral representation. So n is of course a natural number. You have to be some points in R, and well, these ti are obviously, as before, partition of the interval 0 to t. Okay, so this is fine, and now we basically want to show that this class S here is dense in the space of all two random variables which are measurable with respect to the Brownian filtration at the terminal time t. This brings us to the Martinagle, the H2 representation theory, which is proposition 6.2 in the lecture notes. So this is H2 representation. Okay. What does it mean? What does it tell us? Let me formulate it. So I have a random variable in alt H2, L2, right? This is on a probability space, and I wanted that this is actually not F measurable, it's FT measurable. Then my claim is that then there exists integral random process in H2 such that I can represent this random variable X as its expected value plus the Schrier integral of phi with respect to the Brownian motion. Okay, and I also know that if I have two different representations, so phi and psi in H2, such that they both represent, so okay, these are two statements, right? This is number one, and this is number two. They both can use to represent X, then they're actually unique. Oh, the representation is unique in the sense that if we have two different ones, then they are almost surely the same. Again, on the product space. This is actually rather trivial for us now because this just says, okay, we have an iterator process here, right? X is this. We can understand. I can understand this both as iterator process, and then same argument tells us that their representation has to be unique. Okay, so let's quickly do the uniqueness. It's exactly the same argument, as you know. Uniqueness, and then the first statement that the existence of such a phi is much harder, and it's based on the idea that okay, the aim is to show that this class S is dense in the space in the two random variables which are FT measurable. Okay, so what we first see here, uniqueness, okay, if I have two processes phi and psi which are in H2, then the difference is in H2 as well. And then we can use Ito's isometry, which tells us, sorry, this is as first, this of course is 0 because they represent both this random variable X. Right, this here is just meaning X minus X, so X minus 0. Then I use Ito's isometry to show that I need to have this, and this means it immediately implies the claim because this is here non-negative, right? Because we have this power 2. So we know that phi is equal to psi p times lambda almost true. Cool. So this was really simple. And now we need to work for the existence, which is definitely more work. Existence. Step 1. So the first step, we want to reduce everything. I mean, this is based on an approximation argument. So we want to reduce the general L2 case to the finite dimensional approximation. So the first thing we do is we define a set D, which we want to show that it is dense in the L2 space, right? So what we do is, okay, these are FTI. These are functions which are generated by finitely many increments of the Brownian motion. So this f is a function from Rn to R, and it's bounded and measurable. N is, of course, a natural number, and I have here my partition of the time interval. Okay. And this is okay. Can rewrite this by taking, okay, this is just all function g acting on ti up to tn, and g is again a function from Rn to Rn, and it's bounded and measurable, and it's a number, and this is a partition of our interval 0 to t. Okay. And okay, this, why is this true? All right, x xn is just equal to f of 2 times tn minus 1. Okay. And the first thing we want to verify here is D is dense in L2 of Ft. Okay. This is probably a standard argument. You have to show it. And if you want to approximate L2 function, this is what you do. Okay, so let's do so. The first thing is reset here. Let's introduce a class C, which are all A in 0t, such that A is in the closure of D. And we want to show that the closure of D is L2. So this is the closure of D. Closure of D. And with respect to L2. Right, we take the closure with respect to the L2 norm because these are the Hilbert space we are working on. All right, that is actually this simple system here, and this is luckily here's a Dynkin system. System. All right, and it containing Ft for all. Okay. Because it contains the with the finitely many the finite dimensional realization are contained in here. So this contains the system, and this means C is actually the same as the filtration generated by all these FTs. Oh, this has to be 0. Okay. Cool. Right here we have the natural filtration. All right. And this means this is just F P filtration, natural filtration of the Brownian motion. So the only thing which is missing here is the null sets, right? So we work with the completion. What we have here is that actually D is dense in the L2 space if we use the natural filtration. And this means, okay, the null sets, I mean, that doesn't matter for this density argument, it's also dense in, oh, that's not an R, the space, if we put all the null sets in there as well. Okay. Okay, cool. So that's the first thing we have observed. So it's enough to show that our class S, for which we have the Martinagle representation already, is dense in the class D, because D is dense in L2, which allows us now to only approximate these functions which are generated by finitely many increments of the Brownian motion. All right, step 2. Again, okay, let's define 2 classes. The first is dn, right? We want to reduce this further and further to something which we understand. So d is n is, okay, depends on the increments ti, the times ti to tn, and actually these functions here. Oh, right. Which are supposed to be in L2. And they're allowed to complex value. All right, and measurable, of course. And we introduce the Sn, which is the same. I mean, this is S now, depending on the same time points, Ti to Tn, which are the span of the product from from 1 to n of these functionals where we have already a Martinagle representation. U1 up to un. Un. Here, this, okay, it's fixed n and fixed times. So fixed partition. All right. So the goal of in the second step is now to show that Sn is dense in Dn. Right? So further and further want to reduce the general L2 space to the situation which we understand, and for this Sn, we already have our Martinagle representation. And then we make an approximation argument to extend it from the simple case again, because everything is dense, to the general L2 space. All right. Okay, so let's do this. So first thing we note Sn Dn is a closed linear subspace of L2 PT. Right? Yeah. Right. So wait, if I and I can, if I have function random rivals of this form, I can take linear combination, and the closure will only depend on these increments. That's great. And it obviously containing Sn, right? Because Sn here are of this form. Cool. And now what do I want to show is I want to show that if I look at the orthogonal complement with the L2 norm, right, or the L2 distance of Sn and D, and this is actually just the zero element. Right? I mean, they both are linear spaces, so they both contain the zero, but the section is only the zero element. And what does this mean? Okay, this means for all x in Dn with x, well, this is the scalar product on L2, which are 0 for all z in Sn. It follows that x is only 0. Right? Okay, so let's check this. Okay, first, okay. Right, we have here Brownian increments, and the Brownian motion increments are normally distributed. So there's a function p from Rn to 0 infinity, right? Which is the normal, that be the density of what here are Brownian increments, right? This is just a normal. I mean, this is just a normal distribution of this density of a normal multidimensional normal distribution. But I don't want to spell it out here because it's not needed. Okay. Okay, so what do you have is, okay, let's take now an element x as we want to have. We take an x in this intersection of the complement of S and N and D. And we want to show that x is 0, right? This is our goal. So x is in D, so we know that in Dn, so we know it's the form f ti t0 up to time tn minus tn minus 1. And now I want to take an element in Sn, right? This is what I have to do. So I take that, say u. I use just a random number in Rn. So this is just my z is here in Sn. So I have the representation that it's the product from 1 to n of the exponential of iui pti minus bti minus 1. Right, and u is in Rn. So what do we get here? If we, since x is in the complement, we know that x times that u is 0, right? Because they are in, well, they're in the complement sets to each other. And this means, if you spell this out, there's nothing else than the integral over Rn of fx multiplied with the density of xx, right? We're just using that we know the distribution of the Brownian motion. And then we still have here exponential function of I, scalar product of u and x. Right? This is the form which we plug in, right? This is the definition of z, u. This is dx. This holds actually for all u in Rn. Okay. But now we know that this here is a non-negative non-negative function, right? So this means this implies that f times Pn is 0. And this implies, right? Because it holds for all u. I mean, this is just a Fourier transformation, right? This is your Fourier transformation. And if the Fourier transformation is 0 for all u in R, then this means also the function you applied it for is equal to 0 for all f. And this means, okay, since this is positive, as I said, this means f has to be identical to 0, which is exactly what we claimed here. The only element in D which is orthogonal to all elements in Sn is just the function x. So this implies okay, to be consistent with the lecture notes 6.1. All right. And now we know, hence, right, what would you have as if I take the closure of sorry, is this an S? Yeah, this is S. I take then the complement, this is the same as the complement of S. So hence for all f in, let's say, Dn, we have that f is equal to g plus h, where h is in Sn and h is in Sn complement. Right? This is just, I can decompose every element into part which is in Sn and which is in the complement of it. And now using 6.1, so that we know that h is, we know that h here is 0 because the only thing here which is in D and in and the complement of Sn is 0. So this means f is equal to g, and this is in the complement in the closure of Sn. So this implies that Sn is dense in Dn. Cool. All right. So last step is now, okay. Step 3 is what we want to do is now we want to come from the representation which we have for Sn to the general random variables. So this is representation for all x in L2 omega ftp. All right, then. So by step 1, by step 2, we know that S, which is just the union of all these finitely many representation, and then I have here S n's, is dense in D, which is just the representation U same as SNT dn the end, right? And D is dense in the L2 space here. Right. So, okay, now I just do know, okay, if I have now okay, if I have x in L2, D, and there exists sequence xn in Sn, right? Because these are all dense. So D is dense in there and S is dense in D. So I have a sequence in Sn such that Xn approximates X in L2 as L goes to infinity. And our previous lemma, lemma 6.1, for Sn, we have already a representation. Right? So Xn is nothing else than X expected value integral, and then I have a sequence of psi n s dbs. Right. And we know by the L2 convergence, so that xn minus xm is actually a Cauchy sequence in L2. So if we plug this out, well, what is it? Well, there's nothing else, and then okay. Here, let's make it here 2 xn minus the expected value of xm square, right? The cross terms, and they disappear again. And then we have the integral, the 2 phi m minus phi m, both depending on s, dbs squared. And this is by Ito's isometry, right? Okay, I can keep the first term here. And Ito's isometry tells me that, okay, I can get here the square inside. So I have here phi n minus phi m squared as TTS. Okay, so what do I learn from the second observation? Well, from the second observation, I learned that phi n is a Cauchy sequence in H2. That's great. Okay. And from here, then they converge in L2. This actually implies as well, okay, let me make a different color. We know that the integral, they also converge. Right, this is implied by the L2 conversions. So here we go. Right, so this goes to 0, this goes to 0, so we have this. And this means we're basically done, hence we get x is equal to the limit of xn, right? Because the xn's, this is why they're chosen. This is equal to the limit of xn and xn here, yes. And okay, here we know that, okay, we calculate the limit here. So this is just the expected value of x. And we know that these, this is a good phi is conversion A and H2. So they exist actually a limit. So they exist to such that Fn converges to. This is the F we have here, which we get. Cool. And this is all we wanted to show. All right. So now the actual Martinagle representation theorem is a quick corollary of what we have seen proven so far. So there's not so much to do. Let me give it to you. This is the main theorem, even if it's now simple to prove. And this is theorem 6.3, which is the Martinagle representation theorem. Where's the statement? I assume I have Martinagle. So X is a Martinagle. And I need that it's measurable with respect to the Brownian filtration. This is why I recalled it at the beginning of the video. And I want that the terminal time of the terminal random variable xt is in L2. And then they exist an element, an H2 process such that I can represent the Martinagle xt in terms of the expected value of the initial condition, which is just a constant here, plus the integral from 0 to t of phi, yes, for all t. And this representation is actually unique. Is P times the Lebesgue measure almost everywhere unique. All right. Okay. So the proof is now rather simple because we just need to apply the proposition, the previous representation theorem for L2 random variables. So proof. Apply proposition 6.2 to x2, right? This is an L2 by assumption. So this means there exists an element in H2, which is actually unique. P times lambda everywhere it's unique, such that xt is equal to the expected value xt plus, all right. Oh, and now we can take the conditional expectation and use that it's a Martinagle to get that this and the expected value, this is x0, and this is, right, It's in Martinagle as well, so we get here just the integral from 0 to t of BTS. All right, that's it. Thank you for watching the video.